nuclear reaction, the NR. Lovely. And we're gonna focus more on nuclear reactions inside the nuclear power plants. Yeah, this is our nuclear power plant in Czech Republic called Dukovany. It's near to Brno, where I live. Especially we're gonna look on one place which is called nuclear reactor, as you can know, and how, as we can tell, that they are the most reaction occurring just there in nuclear reactor. For our nuclear reaction in power plant, we need some fuel. Yeah, you know, maybe you know that the fuel is our famous uranium. So this is the stuff. This is uranium, nature occurring uranium. So if we put Geiger counter near to this sample, yeah, it's kind of radioactive a little bit here. So this black stuff, it's a uranium oxide, which is used for the fuel. But we must process it a little bit to enrich this, because the most uranium inside the sample is uranium-238. But we need more of the second most common uranium, uranium-235. And this number means if we have uranium-235, this number means how many protons and neutrons are inside the nucleus. So this is, for example, this is our model of uranium-235. So there are 235 particles. These green ones are neutrons, and these orange ones, or what color it is, orangish ones, are protons. And the number of protons is often written in down corner on left, so it's 92 protons. This is our uranium, which is used for to not create, but to have some energy, to make some electric energy or thermal energy, and then electric energy in an electric power plant, nuclear power plant. So we're going to try to make a fission, which is the most famous nuclear reaction, which is occurring inside the nuclear reactor. So we need our fuel, and also we need a neutron. So this greenish balls will be our neutrons. This green one, or this hairy greenish ball here. So now we're going to try to hit our nucleus of uranium and to make it fission, to destroy it a little bit. But we must hit it first with our nucleus. Yeah, but our neutrons are too fast, so we need to make it slower to aim better, basically. And for that, in nuclear power plants, the water is used, because water is basically two hydrogen. So this is our hydrogen. A hydrogen is one proton, or one proton and one neutron. It also could be. And when the neutron hit our hydrogen nucleus, yeah, it slowed down the moving neutron. It comes back. It shouldn't happen, but it happened. So this slows down our neutron, and it could hit our uranium. Now it happens. And the uranium core, the uranium will just destroy it. This is called the fission. And after this reaction, the 2 or 3 or sometimes 1 new neutrons just start moving around from the from this fission reaction. And also, two new elements, two new isotopes of some elements are creating also. And thanks to the neutrons which are leaving our atom, we can continue this process again, and this takes us to our another model. So this is the line where the neutron, which will travel to our near to our uranium nucleus. So we try our nuclear reaction a little bit, and we can see that there will be more and more fission reactions with neutron and also with uranium. And with this reaction, the energy is created. And if we don't control it like this, as we see, the principle of nuclear weapon will be there. So this is something what we don't need. We don't need that much energy. We need to increase the creating energy. So we need some element or something to catch the neutrons. And we use the control rods, which are created from material boron. This is a nucleus of boron. And if we just if the boron meets our neutron, it will catch it, and then the neutron can't make the reaction with the uranium. Yeah, here it is. Sorry. Here it is. Boron. So this is it. So we can put to our model of chain reaction a little absorbator, which is the boron. And now we can see that the reaction is more controlled. It's not that wild. Yeah. So this is something what we need. So let's go to the board, because we can describe it with a little bit of equations, which is a lovely thing in physics. And these were the reactions with neutrons, which is one neutron and one neutron and protons and 0 protons, basically. We see the fission reaction, fission reaction, which is creating that we smashed our uranium atom, the uranium nucleus, to two pieces. And there, if we write it down, there will be uranium plus neutron, and it leads us to krypton and barium and some number of neutrons, for example 3, 2 or 1 neutron. So we can put it right this in these equations. And if we write down the atomic and nuclear numbers, we can have it like this: 235 and 92 and 10. So this is our fission reaction, but the products of this fission reaction could be different also, because we don't know how we just smash the nucleus. So basically almost everything lower than uranium could be created theoretically, but everything is about probability when some elements are created. And also we got the capture with the boron, capture reaction, which means there was a boron with 10 protons and neutrons, and we just hit it with neutron, and it led us to boron 11, which is also stable, and some remains energy just vanished with some gamma rays. And there was also the scattering, which means that the nucleus scattering reaction, which was occurring when we slow down our neutrons. So this was also the reaction. So these reactions are the basic principle of nuclear reaction inside, or nuclear reactions inside the nuclear power plant, inside the nuclear reactor, inside of it. This is the amazing schematics picture of nuclear reactor. The fuel rods. In fuel rods, the fission reaction is taking place. In a moderator, which is mostly water, the scattering reaction is there. And inside the controlling rods, the capture, neutron capture is there. We can find it right there. If we are talking about energetic field, another nuclear reaction is important, a lot of important, and is a fusion reaction. So fusion. So fusion reaction. And it means that we don't break atoms, we don't break a nucleus, we combine them. So we got one hydrogen, the heavy hydrogen, super heavy hydrogen, and the hydrogen, the heavy hydrogen, and it will fuse together and another energy is created. And the one neutron will leave this reaction. So this is maybe the future of energetic, and this maybe will be a future way to make some electric energy. Nowadays, this fusion reaction is occurring in the sun, and this is where our sun makes energy or have energy. And we can end this performance with a little bit reaction, not nuclear reaction, not a real nuclear reaction, but with chemical reaction with hydrogen. Because for demonstration how much energy is in hydrogen, we can use it for chemical reaction. In this balloon there is a hydrogen, and we can start this reaction with a little bit of fire. So embrace yourselves, take your earplugs or anything, and this is gonna be loud. Yeah. So prepare for everything. So 3, 2, 1.